Suppose that a particle A moves from point A to point B in a straight line. A constant force F acts on the particle. So what is meant by a constant force? Well, what is meant by a constant vector? Well, it's a vector that never changes direction or magnitude. So, as the particle moves in a straight line from A to B, we can see this force F acting on it never changes. Now, there are a few points worth emphasizing, I think. The first point is that this force F does not have to be the resultant force on the particle. The reason why I say this is because I've used the letter F to stand for the resultant force in previous videos. Another point is that there could be many forces acting on the particle. We could have a complicated array of forces acting on this particle, but we are not interested in those forces. We are only interested in the work done by this particular force F. Another important point is that the motion of the particle does not matter. What do we mean by that? Well, we know that the particle is going to move in a straight line from A to B. That's the only situation that we will consider. But how quickly it moves does not matter. So it could move slowly at first, then it could speed up, then it could slow down, then it could speed up. It doesn't matter. It also could just move at constant speed from A to B. So the speed of the particle in its straight line journey from A to B does not matter. It does not affect the work done by the force on the particle. Okay, so let's see how to get the work done by this vector F. We want the component of vector F in the direction of AB, that's the direction of motion, and we want to multiply that component by the distance travelled by the particle from A to B. Now, let's suppose that F has magnitude 4 newtons and that it makes an angle of 60 degrees in the direction of motion of the particle. So we measure our angle anti-clockwise from the direction of motion. So to get the component in the direction of AB, we have to multiply 4 times cos 60 degrees. And we must multiply that component by the distance between A and B, which is 3 meters. Now, I will refer to the work done by force F as W, and I've put in the units here. Force is in newtons, distance is in meters. So when we multiply this together, we get the unit Newton times meter. That unit is called a joule. Now, if the force has a component in the direction of AB, as this one does, its component is pointing in the direction of motion, then this force does positive work on the particle. Okay, because the cos of 60 degrees is a positive number. Soon we will look at an example of a force that does negative work on a particle. When a force does positive work on a particle, it means that the force contributes to the energy of motion of the particle. And we will see more about the energy of motion of a particle in a later video. Now, here is an example of a force that takes from the energy of motion of this particle. Remember, the particle moves in a straight line from A to B. Now, what causes that motion is not important. Well, it's not going to be this particular force, because you can see that it's got a component in a direction that opposes the motion of the particle. So, as I said before, we don't know exactly what forces are acting on this particle, and we are not interested. All we know is that particle moves from A to point B in a straight line, and we just want the work done by this force. Now, the direction of motion is this way here, so we measure our angle anti-clockwise from that direction to the vector. So here, as you can see, we get an obtuse angle. Let's get the component of this vector in the direction of motion. Well, you can see what's going to happen. The component is pointing in the wrong direction, if you like. How do we get its magnitude? Well, we can multiply the magnitude of this vector by the cos of this angle here. Well, this angle, as you can see, is 60 degrees. So we can multiply 4 by cos 60. Well, if we do that, we get a positive answer. But to emphasize that we get a negative value here, we should always multiply the magnitude of the force by the cos of this angle here. Well, we don't have to, but this will automatically come out to be negative. So the cos of 120 degrees is minus a half, so our answer is minus 6 joules. So the work done by this force is negative. That means that this force takes from the energy of motion of the particle. Let's look at this example here. We have a force of magnitude 4 newtons. You can see that the angle between this force and the direction of motion is 0. So we can multiply the magnitude 4 by the cos of 0. Well, we know that the cos of 0 is 1. So we're just going to get 4 for this. And that's multiplied by the distance 3 meters. So we get 12 Newton meters, which is 12 joules. So here we are working with a force that has the same magnitude as before, but you see that we get 12 joules of energy. Well, more accurately, I should say that the particle's energy of motion increases by 12 joules. Let's take one last example. Here we have a force of magnitude 4 newtons. Well, there's nothing special about the magnitude of the vector. We want the angle between the direction of motion and this force vector. Well, we can see that it's 180 degrees. The direction of motion is this way. Now the cos of 180 degrees is minus 1, so as we expect, we get an answer of minus 12 joules. So this means that this force F takes 12 joules of energy from the particle's motion.